Now I'm going to shift gear. So goal is to show the equivalence between this worldline theory and space-time QFT. So we should head towards asking questions, what it takes one to prove such an equivalence. So in order to do that, the discussion will be facilitated by some diagrammatic component tool in the argument. So that's what I'm trying to introduce now. So there is a diagrammatic representation, of the object that we found in this theory, which is a two-point function. So this is equal to delta x minus y, or k. Delta and k are same for us only up to a phase, and this is x and this is y. So it's like a propagator. You must be familiar with that from your QFT1 course, and so we can represent this quantity by such a diagram where you have two external points and there's a link between them. That's a propagator. So it's a response moving between x and y in a time-ordered fashion. And so given a diagram like this, correspondingly there is a mathematical expression. So of course this is not an equality, it's something, let me put it like this. So given the mathematical expression is equivalent to this diagram and vice versa. So this is a rule to convert a diagram to a mathematical expression. Rule to convert a diagram to a mathematical expression. And such a rule is we will generically call it a Feynman rule. Now, what kind of diagram is it? The diagram here, so if you want to look at it more closely, what exactly I'm doing here is a topological diagram obtained by connecting external points by lines. So this is a topological, I'll explain the terms, topological diagram obtained by connecting external points by lines. The quantity, the mathematical quantity that Feynman rules gives, ultimately this mathematical quantity, that depends on certain argument, and this argument is nothing but this external point. So this external, anything that is internal will not show up in the final expression. The expression depends basically on these external points. So so these are the variables on which math expression depends. And these type of diagrams are called Feynman diagrams. So now let me explain what this topological means, topological diagram. So let me line here to explain it here. So what a topological diagram means. So a topological diagram is that rule is that you take the external points and connect them by lines, but then you can draw infinitely many such diagrams, but I'm drawing only one diagram. So what it means is that any two diagram, if you take two diagrams which have the same set of external points, but can be deformed, one can be deformed to the other, then they are counted as same diagram. So that is a topological equivalence. So all diagrams all diagrams with same set of external points that can be continuously deformed to one another are topologically equivalent. So it means, for example, this diagram is same as this one, which is same as, say, this one. So the same x and y have to be same, and so on, right? So you get the idea. Now, then we saw that in our worldline theory, we get a diagram like this. Okay. Now, why is it important? It is important because what we are going to show is that the theories can be classified by set of diagrams. So the statement, let me begin with the following statement. A theory admits a set of Feynman diagrams. A theory admits a set of Feynman diagrams, which means that what we mean by a theory is equivalent to a set of allowed Feynman diagrams. Now, in general, a theory, the idea of a theory is that you have a mathematical structure where you can do all possible computations. So a theory actually should be given by our normal sense that it has a set of all possible computations. These two things are not, they look like very independent, and this equivalence between a theory and set of allowed Feynman diagrams is something that looks like non-trivial, and we should explain what it actually means. So this is what I would do now. So this is like an assertion to be explained further. Okay, what do we actually mean? Because on one hand, we understand that theory is like set of computations, and when you specify something that naturally what we can compute in that theory naturally follows, and then you are making another claim that there's an allowed set of topological diagrams, and how these two things are synonymous. So let us look at what kind of computations we can do. So one result we have in our reserve is that worldline theory, it's a specific theory. Worldline theory has in itself the diagram like this. This we have already seen, okay? So we are taking worldline theory as an example where we are trying to demonstrate this fact. So we know worldline theory already has this computation, basically the computation of this path integral, and that has a diagrammatic representation. We just introduced that. The question is that what else could we compute? Compute in this particular theory. And the answer is that there are two things that I'm going to discuss. Is that one is insertions, and two other. So this, you can view these as a process. You can view this as a process, a particle moving from one point to other, and so other possible processes. So question is that what are the, so I will explain what I mean by insertions. In this second point, what other processes, that's a more physical way of asking this question. This is basically a mathematical expression. We have interpreted that, we have given a diagrammatic representation to that, and then there's a physical interpretation. What process does it describe? A theory, in a sense, is a complete structure that describes various processes. You could view it that way as well. So what other possible processes that you could describe using this tool, using this path integral and that particular action? Okay, so let me discuss that one by one. Okay, let me end this slide here.